Hello, Chem 120 students. We're back. Clap of joy with lecture 2 of our gas chapters. So this one, I promise, will be a little bit shorter than the last one. We really covered a lot of territory in our last video lecture. So just to kind of recap, because we did cover so much territory, I want to go over those gas laws just so you have them all in one place and you can kind of compare them with your notes that you might have taken from that lecture. So the first gas law that we talked about was Boyle's law, which is talking about the relationship between pressure and volume, and we know that that is inversely related, which means as one goes up, the other would go down. So our working equation that we're going to use to compare two systems where one variable is changing and we're asked to find information about the other variable is P1 V1 equals P2 V2. All right, so that's Boyle's. Then we have Charles's law. Charles' law is the direct relationship between temperature and volume, which means as one goes up, the other also goes up. Remember that for all of these first laws, every other variable is being held constant, which is the only set of circumstances where these laws hold true. So in Charles's law, we know that pressure and the number of moles is staying the same. In Boyle's law, we know that the number of moles and temperature are staying the same. Then we have Avogadro's law. That's an A. Which is that the number of moles is directly proportionate to the volume. Again, temperature and pressure are staying the same. And our working equation there is V1 over N1 equals V2 over N2. So these are really useful when you just have one thing changing and you're asked about the effect on the other variable. If you have multiple variables changing, you're going to need to use the ideal gas law, which is PV equals nRT. Remember, R is 0.08206 liters atmosphere per Kelvin mole. So because those are the units for our constant, those are also the units that we're going to need to make sure all of our variables are in so that they cancel out. So there's really two times where you'll be using the ideal gas law. One instance we'll have a nice example of in the next slide. That's where you're given, for a different example, let's say you're given pressure, you're given volume, and you're given temperature, and you need to know the number of moles of a gas in that under those conditions. That would be one example of using the ideal gas law. Another example would be if you were given the pressure, volume, and temperature under one set of circumstances, and then the change involves both, let's say, volume and pressure changing. We can't use Boyle's or Charles or Avogadro's in order to assess that. We can only use the ideal gas law because we have multivariable changes. That, wildly, is a recap of everything that we did in our last lecture. Awesome. Okay, so let's keep moving. So the next big piece of learning that we have is really just an extension of Avogadro's law. And that states that if you had 1 mole of any gas, any ideal gas, it would occupy 22.42 liters at STP. You can just think of that as 22.4, that's fine. So what's important is that this is specific to STP, and we're going to prove that it's 22.4 liters in a second. But STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, which you should immediately at this point be thinking that's 273 K. And standard pressure is 1 atmosphere. All right, so let's apply the ideal gas law to see if 1 mole really would occupy 22.4 liters at STP. So ideal gas law, again, we have PV equals nRT. Here our pressure is 1 atmosphere. Volume is what we're solving for, and would be 1 mole. Remember, of any ideal gas, it doesn't matter what its identity is at this point. R is that 0.08206 liters atmosphere Kelvin mole. And T is that 0 degrees Celsius, otherwise known as 273 K. So now we want to rearrange PV equals nRT in order to isolate volume to one side of the equal sign. That's just a fun little line I just drew. So volume would be equal to 1 mole times our 0.08206 liters atmosphere per Kelvin mole times our temperature of 273 K divided by 1 ATM. So go ahead and plug that into your calculator and let me know what you get. I get 22.4. All right, so that's pretty cool. We now know that any gas at STP 24 or 22.4 liters is going to be the volume occupied by 1 mole. This should look a lot like a conversion factor because that's what it is, and we're going to be using it in gas stoichiometry. But before we get there, let's just use this slide to kind of illustrate this big idea. So here we have 4 balloons, and the balloons are under the same conditions of pressure and temperature. Now, if you look, we have argon, which is a noble gas. It's quite large, pretty complex. We have our methane, which is, again, a pretty complex gas. Then we have hydrogen, which is really, really simple, right? Small atoms. There are molecular diatomics. And then we have nitrogen as well over here. So it doesn't matter that there's differences in size of the individual molecules or there's difference in complexity. All that matters, because we're looking at these as strict ideal gases, is that we have the same number of molecules under the same pressure and the same temperature, which means that they are going to exert the they're going to occupy, the same volume space. So it's kind of a hard concept to wrap your head around, but then once you do and you really think about what it means to be an ideal gas, it makes a lot of sense. Also think about it in context of Avogadro's law. It is only by virtue of the fact that we're talking about ideal gases where their individual volume is negligible that we're able to make these comparisons between, or direct comparisons, between number of moles and volume. This next figure is just ridiculous. It's from an older edition of your textbook. And that woman is so happy to hold that box. That's apparently 22.4 liters. Does that illustrate a concept? Sure. Why not? I thought it was worth keeping in. Uh-oh. Now I'm typing. There we go. Okay, so let's solve a problem and also recognize that maybe boxes aren't spatially your favorite and you're more of a sphere kind of person. Now you can see that this beach ball would also be 22.4 liters. Crazy. Just, it's a wild, wild world, right? Okay, so we have this question. What is the volume in liters occupied by 49.8 grams of HCl at STP? So you might not know this yet because we just learned it. But anytime you see this, STP, you should be like, yeah, I'm happy about that situation. Why? Because we know that if a gas is at STP, we're going to be able to use molar volume, which remember is that relationship of 1 mole being equal to 22.4 liters. Really big idea, only true at STP. Okay, so let's go ahead and solve this problem. So the first thing you should notice is that we have 49.8 grams, right? And anytime we have grams really at this point in the class, we're gonna get out of grams and get into moles. I'm just gonna let that disappear because it's really, really ugly. Okay, so 49.8 grams of HCl. All right, so we need to find the molar mass of HCl. So we know chlorine is 35.45, so that would be 36.45 grams of HCl in 1 mole of HCl. So let's go ahead and plug that into our calculators and see what we get. I'm only doing this on the video so that you have time to do it at home, right? Yeah, 1.37 moles of HCl. So we have 1.37 moles, and regardless of what gas it is, it would have this relationship at STP, which is that 1 mole would occupy 22.4 liters. And you get 30.7 liters. Yeah. Love it. All right, so that's a pretty simple example of how to use molar volume. You're gonna have a number of gas stoichiometry problems. There's a couple in your practice work. There's also some gas stoichiometry on your homework. Luckily for you, there's a ton of practice and recitation. So don't sweat it, but you do need to get some practice. You're gonna have to remember all of the principles that we learned in chapter 3 and 4. What I mean by that is the method of problem solving in stoichiometry, and the considerations that you always need to have in stoichiometry, like limiting reagents and percent yield. Right, so if that sounds like gibberish to you, do some review. Okay, so here is a nice example where I feel like I used this on a former exam and my students were like, "We hate you," and I was like, "Come on, it's so good." And then I decided not to ever use it again. So here's our problem. We have urea is used extensively as a nitrogen source in fertilizer. Classic SAM fun fact on an exam question. It is produced commercially from a reaction of ammonia and carbon dioxide. Again, welcome to my class. I think science is really cool. Ammonia gas at 223 degrees Celsius and 90 ATM flows into a reactor at a rate of 500 liters per minute. Carbon dioxide is at 223 degrees Celsius and 45 ATM. It's flowing into a reactor at a rate of 600 liters per minute. What mass of urea is produced per minute by this reaction, assuming 100% yield? Right? So that's like a classic, I'm gonna puke, I'm a student, I hate SAM question. But the exact same, this is actually what I think you guys think. I'm sorry. The exact same problem solving strategies that we've been using this entire semester are going to apply here. So let's break it down like we've done in other problems where we have the, excuse me, let me get rid of that. Where we have our ammonia and our carbon dioxide, and we're just going to define what variables we have. Trying to pull out these numbers from the word problem and start to build greater context in how they're going to be relating to each other and how we're going to use them to solve our problem. Okay, so we have ammonia. And the conditions for ammonia is a temperature of 223 degrees Celsius. I'm going to keep my pen here so it doesn't disappear. And let's just go ahead and immediately change that to Kelvin, which is 498 K. 96, sorry. Right? Always check my work. Why not? Okay, and then we have a pressure of 90 ATM. Ooh. Flowing into a reactor at a rate of 500 liters per minute. Okay, so we've never seen a problem in this chapter using rate before, but right now, instead of just being intimidated by a new unit, we're just going to move forward, continue assigning our variables, and see if maybe in the end it doesn't kind of go away, right? Classic avoidance. Okay, so now we have carbon dioxide, also at a temperature of 223, otherwise known as 496. Okay. The pressure of our CO2 is 45 atmospheres, so lower pressure than that ammonia. And it's flowing into the reactor at a rate of 600 liters per minute. Awesome. Okay, so we are given information about ammonia, and we're given information about carbon dioxide, and we're asked for information about urea. This should be ringing alarm bells in your head where you're thinking, what is my limiting reagent? Right? One of these things is going to run out before the other. Which one is it? That's just a fat T. Sorry. Reagent, yeah. Okay, so we need to figure out what thing's gonna run out first. And we have temperature, we have pressure, and we have a rate. Okay, so let's just figure out exactly what are we solving for. What mass of urea is produced per minute by this reaction, assuming 100% yield? Well, all of our rates are given as per minute, so we can actually just think of that as 500 liters, because that's how much is produced in a minute, and all of a sudden our rates just become volumes, right? So I'll just rewrite that really quick so we have a little bit more room. So our variables again, in H3 we have a temperature of 496 K. We have a pressure of 90 atmosphere. We have a volume of 500 liters, right? Because we're asked how much is produced in 1 minute, and our rate was in terms of per minute. Temperature is the same. Pressure was 45 atmosphere, and our volume here is 600 liters. All right, the only way we're going to be able to solve this is with an ideal gas law for PV equals nRT. So PV equals nRT. That means that pressure volume over RT would give us the number of moles. So for NH3, we have our 90 atmosphere times our volume of 500 liters divided by R, 0.08206 liters atmosphere, Kelvin mole, don't forget your units, times the temperature, 496 K. All right, plug that into your handy dandy calculator. 90. Why do I always say handy dandy calculator? It's so weird. I love that's the thing that I'm questioning about myself. Okay, so I get quite a few moles. This is going to be 1,105.6 moles. All right, let's do the same thing for CO2. So we have our pressure of 45, our volume of 600 liters, we'll plug this in 45 times. That can't be right. So I got 663.4. I'm just going to double check my math because I have the sneaking suspicion that I did something wrong. Yep. No, that's right. Okay. So now we can look at our mole relationships between the amount of ammonia we need versus the amount of carbon dioxide to figure out what our limiting reagent is. So remember, one of these things is going to go away before the other. One of them is going to restrict the amount that we can make because it will run out first. That thing is called our limiting reagent, right? This is all old hat. So if you look at our relationship between ammonia and carbon dioxide, we have a 2-to-1 ratio, which means that we would need to have twice as much ammonia to carbon dioxide in order for the ammonia not to be our limiting reagent. So if you look, we can see that we don't have twice as much ammonia to carbon dioxide, which means that we're going to run out of ammonia first. If that doesn't make sense, then by all means just solve this out the long way, like we've done throughout all of chapter 3. That's the approach that we took. But at this point, I'm going to just go ahead and say, okay, we know that this is our limiting reagent, so we're going to move forward with our analysis, given that we have 1,105.6 moles of NH3, and we know that NH3 or ammonia is our limiting reagent. So I'm going to give us a little bit more space here. Hopefully you've got that down. All right, so our question asks us what the mass of urea is, which is kind of annoying because now we have to find out the molar mass, but whatever, it's good. So we need to use our mole ratio taken from our coefficients of our chemical reaction. 2 moles of NH3 for every 1 mole of urea. 1 mole of urea. All right, let's see. What is the molar mass? I have 60.06. Yeah, that sounds about right. All right, so let's go ahead and plug that in. And I get cool. So there we go. That's how much urea is produced. Fun facts, right? There's a lot of gas stoichiometry problems in your recitation as well as in OWLs and on the Chem 101 homework. So you have a ton of opportunity. This is probably the hardest question that you will encounter. Hopefully it does a good job of illustrating why STP is really cool, because then you can just figure out so much so quickly. But it's good to get a nice review. All right, so that's that slide. Okay, another law that we're interested in is called Dalton's Law. So Dalton's Law, I think it's a pretty simple principle, but the applications can be a little challenging to wrap your head around. So what Dalton's Law of partial pressure says is that the total pressure of a chamber is going to be equal to the pressure exerted by each of the gases. So here we have one gas in a chamber, another gas, and the combined pressure, which is they're trying to show with these weights on top of the piston, is the total pressure is equal to the partial pressure of each of those gases, right? So we needed 2 weights to counter the pressure of these gas molecules. This we needed 2, 4, 5, and the total pressure here would be 2, 4, 6, 7. Okay, so there's two equations here. You can just add your pressures to find the total pressure, or this other equation, which is the one that you'll more frequently end up using, is that the total pressure would be the number of moles added together times RTB. Obviously, these are under the same temperature and volume, okay, because they're in the same chamber. Okay, so our next slide is a good example of that. So in scuba diving, you have a mixture of gases in your tank. Here we have helium and oxygen. For a particular dive, we have 46 liters of helium at 25 degrees Celsius and 1 atm, and 12 liters of oxygen at 25 degrees Celsius and 1 atm. And they're pumped into a tank with a total volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. Okay, this is fun. Okay, so let's go ahead and work through it. So the first thing that we need to do is figure out how many moles we have of each gas. And then we'll be able to work from there and look at this kind of change in our circumstance in order to determine how many, what the pressure is of each gas. Okay, so this is kind of the long way around, and then I'll show you a nice shortcut. All right, but this is a nice opportunity to use PV equals nRT. So we're trying to figure out what N is, our number of moles. Oop, sorry, forgot to change to my drawing tool again. So we have PV equals nRT. So let's solve for N. N is going to be equal to PV over RT. So we have two gases. We have helium, which is a volume of 46 liters. The temperature is 25 degrees Celsius. All right, immediately converting to Kelvin. Ouch. This is the one problem with this recording program. Let's do it again. So N is going to be equal to PV over RT. I'm so sorry. But this is good. Now you can work ahead of me and you can use PV equals nRT to solve this. Volume, 46 liters. Temperature, 298 K. Pressure of 1 atmosphere. Then we have our oxygen, where we have 12 liters. Ooh, that's ugly. Temperature of 298 K, and our pressure of 1 atmosphere. All right, so let's go ahead and figure out how many moles we have so we can figure out what our overall pressure is. So we need to take N is equal to our pressure, 1 atmosphere, times our volume of 46 liters over R. That says liters atmosphere per Kelvin mole. Temperature of 298. All right, let's plug that into our calculators, and you should get 1.9 moles of helium. Okay, then we have the number of moles of our oxygen, right, using that subscript of O2 so we can keep our two works apart. So 1 atm, 12 liters, 0.08206. Plug that in. Okay, so now we know our individual moles that we had to begin with, right? So we had these two tanks, separate tank of helium, separate tank of oxygen. Now we know how many molecules we had in each tank. those tanks are being combined into a new environment where the total volume is 5 liters, right? So that's much smaller for helium and quite a bit smaller for oxygen as well. So the new environment is going to take all of those molecules and pump them into a 5-liter space. So this question asks us the pressure of each gas and the total pressure. So we kind of have to solve this a little long-winded, only because it asks us for the pressure of each individual gas. And then I'll show you, I'll never ask you to do that, but I'll show you another way to solve this if you just need to know the total pressure. So now we know the number of molecules being pumped in of each kind of gas. So now we need to figure out, okay, well, what is the pressure given that we have the pressure that that gas is contributing, given that we have this new environment that's only 5 liters. So now we need to solve for volume. So we have PV equals nRT, which means volume, or excuse me, pressure, we're solving for pressure, would be nRT over V. So many variables. Okay, so let's find our pressure of HE, which would be equal to 1.9 moles of HE, otherwise known as helium, R, and our temperature, 298K, right? That's not changing. And our volume is 5 liters. And I got 9.3. And that is the pressure that our helium is contributing. So we also have the pressure that oxygen is going to contribute, 0.49 moles. Totally says liters atmosphere per Kelvin mole. Okay, so those are the partial pressures that those individual gas molecules are going to be contributing to our 5-liter chamber. The total pressure of our chamber is going to be the sum of those gas particles because they're all in the same environment, right? So P total is going to be equal to 9.3 atmosphere plus 2.4 atmosphere, giving us a total of 11.7, yes. Very cool. Okay, so that was the way that we had to solve it because we needed to know the partial pressures, right? But if you only needed to solve for what the total pressure is, that's when you get to use that really nice P total being equal to N total times R times T over V. So before we had, let's see, the number of moles of our helium was 1.9. Number of moles of our oxygen was 0.49. Will be good. So if we wanted to solve this without finding the partial pressure of each gas, all we would have to do is say 1.9 mole of HE. Oh, shoot, I don't want that to be there. Let's just make this a really big plus sign. Plus our 0.49 moles of O2, right? We're adding those things, times R, times temperature, which was 298 K, over our new volume of 5 liters. So plug that into your calculator, remembering that that is 1.9 mole plus 0.49 moles, and you would get that same answer. Right, because what's causing the pressure? The total number of molecules that are bouncing off the chamber. The chamber is 5 liters. Yeah. Okay, so now we just have one last little piece, and I think I was true to my word, and this video is going to be shorter than your last one. So we have 2 principles that we need to be able to distinguish between. One of those is diffusion, and the other is effusion. So diffusion, I'm never going to ask you any questions about, but we should be pretty familiar with that. It would be the mixing of gases, right? I'll just leave it at that. Mixing of gases. Think about opening a pizza box in a classroom, right? It doesn't take long before everybody's smelling pizza. That is due in part to diffusion and also to air currents. Effusion is the passage of gas through an orifice into an evacuated chamber. So this is a nice illustration. I always used to use the illustration with my students of alien resurrection when Ripley kills that one alien by getting like sucked out into space. And I thought, oh my God, this is finally my chance to embed a video and just show my students. And then I watched it again and I was like, oh my God, that is so disgusting. So I couldn't do it. But you could Google it and I would only tell you that I warned you. Okay, so it's this idea of you have a vacuum, right? You have this concentration of gases over here. You are going to have them bouncing off the walls of their chamber. Eventually, one of them is going to go through this pinhole and start to fill our vacuum. Cool. So space is a good illustration of that, right? So this is the big kind of law or rule that we want to think about, and I'm not going to have you do any quantitative analysis of it, but I do want you to know this relationship. So it's that the rate of effusion is inversely proportionate to the square root of the molar mass of the gas, right? So effusion and a fancy M, not to be confused with a not fancy M for molarity, stands for molar mass. So what that really means is that the higher the molar mass of a gas, right, I'm going to use fancy M, molar mass, it's going to be the slower, the lower the rate of effusion. Right, and that has to do with kinetic energy and velocity of a mass in motion. So if you, in a hypothetical universe called like a future exam, had a list of gases and were asked which one would effuse the fastest, it would be your lightest gas, and which would effuse the slowest would be your heaviest gas, right? Think about inertia and the fact that gases are governed by physical laws. Okay, so that's just a fun fact. And then I just want to close the lecture by saying that, we've been really restricting our view of gases to ideal gases. I am in no way, shape, or form an expert in gas chemistry. And it gets, of course, much more complicated from here. But this is just a nice introduction and a way of starting to conceptualize the behavior of gases. So it is important to recognize that ideal gases are a hypothetical concept. No gas is exactly ideal. We have been restricting our observations and our analyses to situations where gases are going to behave mostly ideally. There are opportunities, like at a very low temperature, where gases are going to be slowed down quite a bit, or at a very low pressure, where the attractions between gas particles are no longer going to be negligible. And there's other situations where these postulates that we have in the KMT are not going to hold true for that gas in that environment. But it was still useful to think of gases ideally, and most of the time when we're working with gases in the world, not in a synthesized or created system, they're going to be behaving mostly ideally. So that is our exploration of gases. The next chapter is going to be looking at thermochemistry, which is kind of an introduction to thermodynamics, which is very cool.